Hi and welcome back. So in the last video, we had been doing a bunch of different electron configurations, and we found out that we did, I think, this column. And by the way, I think in a previous video I had mentioned that this whole family was called the alkaline metals. And I actually found out the alkaline metals does not technically include hydrogen. So the alkaline metals is essentially everything from hydrogen down. So lithium, sodium, potassium, rubidium, cesium, francium. All of these metals are considered the alkaline metals, and hydrogen is excluded. However, what we found is that all of these elements, the alkaline metals and hydrogen, in the last video we found out that all of these have one valence electron. So all of these elements have all got one valence electron. We also found in the last video that all of these elements over here, this family starting with oxygen, and I've sometimes heard this family referred to as the chalcogens, although I'm not too sure that that's a common term. I've also just heard it referred to as the oxygen family or the oxygen group. But this whole group of elements over here, starting with oxygen at the top, we found out that these all had six valence electrons. And one of the things that I guess I kind of said that it might be a good idea for you to do before starting this video is maybe go through this column, maybe go through our alkaline earth metals and figure out how many valence electrons all of the elements in this group all have. And you only have to do a couple of them to figure out, and hopefully you did that, because I'm just going to tell you right now that all of these have two valence electrons. And then another group over here, maybe you might be starting to see a pattern. And keep in mind, we're only concerning ourselves right now with the S block over here and the P block. We're sort of ignoring the D block. We'll talk much more about the D block in the future. But maybe you can see if you did a few electron configurations for these elements over here, you would hopefully find out that all of these have three. They all have three valence electrons. Or you can also think about that they have three electrons that are available for reaction. They have three electrons that are going to react. And then we'll move over to the next family, to this family that starts with carbon. They all have four valence electrons. Excuse me. Then right next to it, the family that begins with nitrogen. Circle this. This whole family, they all have five valence electrons. Oh, excuse me. I'm still not over my cold, as you might be able to hear. Over here, this next group, this group that starts with fluorine, which is, if you remember the name of this group, and this is a name that's good to remember, these are the halogens. The halogens over on this side, these all have seven valence electrons, and that is pretty important to remember. And then finally, all of the elements over here. And remember, this is our noble gas family. And helium is included in the noble gas family. And we will hopefully in this video get into why helium is included in the noble gas family. Even though, how many valence electrons does helium have? Well, let's just do helium. What is helium's electron configuration? Well, it's just 1s2, right? So how many valence electrons does it have? Well, it has 2, right? So that is, you could imagine, and I'll actually just start erasing a little bit here. That's why, back when we were doing electron configurations, I'll actually maybe cross helium off right there and put helium right here. Helium. That's why helium, we put helium over here in our S block, or it's one of the reasons we put helium over here in our S block when we were doing electron configurations. What we're hopefully going to find in this video is that helium does have very similar properties to our noble gases, and hopefully I'll be able to let you know in this video why that is, and if not this video, it'll be probably in the next video. But anyway, we can see that all of these elements over here, the elements starting with neon and going down, so all of these noble gases, how many valence electrons do you think all of these have? Well, they're all going to have 8. And actually, you know what? I am going to just start erasing a little bit. And, sorry, this might take a little bit of time. I just want to maybe clean up some of these notes that I've made on my page. So I didn't realize that writing out valence would take up so much room. There we go. So I'll say this over here are alkaline metals. They have 1 valence electron. This boron family, they all have 3. And our oxygen family, which I think I use this color, they all have 6. So these are the number of valence electrons that all of these groups have. So the group starting with hydrogen has 1. This group that starts with beryllium, or you could say it starts with helium, they all have 2 valence electrons. Group with boron has 3, carbon has 4, nitrogen 5, and yada, 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 all the way over to the noble gases, and all of, you could say, are noble gases excluding helium, and they all have 8 valence electrons. And what we're going to find is that you should, and this is exactly, I made a video a while ago about how chemistry professors love to use this word. They love to use the word that some atom wants to do this, or some element wants to have an electron configuration. And this is probably in your history class. And this is in your chemistry class where you are probably going to hear this word want, or that an element wants to do something more than anywhere else in the class. Because what we're going to figure out is that, and I am going to use this word too, is that these elements, that the most stable electron configuration, and you can kind of maybe imagine for yourself a little bit about why they are the most stable electron configurations, and you could say that, I like to use the analogy, or anyway, the most stable electron configurations on the periodic table are going to be these noble gases. And you can kind of imagine the analogy I kind of like to think about is imagine a car. Or actually, no, don't imagine a car. Imagine a bicycle. So imagine a bicycle. And let's say we've got our bike wheel. So I'm not going to draw out the whole bicycle. This is just going to be a wheel. So there's the center, and we've got all of our spokes. And let's say that sometimes, I know not all bicycles have this, but let's say we had a bicycle with a reflector. If you've ever seen one of these reflectors on a bicycle, they're these things that, if a car light hit the reflector, or if the light from a car light hit the reflector, it would reflect back and let someone know that a bicycle was riding in the street, I guess. But a bicycle reflector might look, I don't know, I'll just say that'll be my reflector. And maybe if you're like me and you're into cycling, and you maybe saw some of the Tour de France or any of those cycling events, you saw that the serious cyclists don't have these reflectors on their bicycles. And you can think about, well, why is that? Well, this bicycle wheel, it's going to be turning. It's going to be turning really, really fast. So what happens when you have something that's not balanced on the other side? Well, the whole thing is going to, draw some lines. It's going to shake, right? It's going to shake, and it's going to vibrate from side to side, because this whole wheel is going to be turning really fast. And you can say that a reflector, even though it's, it's a small piece of weight, is going to be one piece of weight on one side that is going to be causing the entire wheel to vibrate and shake, and it's just going to make the entire bicycle less efficient. But how about this? What if we balanced? What if we were able to balance, I'll switch colors, with another reflector right on the other side? And say we had a few more reflectors over here, like that. We were able to balance out all the reflectors on our bicycle wheel. Well, if we did that, we would get rid of all of this, just erase the shaking, because we wouldn't shake anymore, because we had balanced out all of the reflectors. And this is hopefully hopefully this analogy is working for you. But you could imagine that maybe an element like lithium, or actually let's use maybe an element like sodium. Maybe sodium's electron configuration, if we use the same analogy of a bicycle wheel with all of these reflectors on it, you can just think of a reflector as like maybe a little piece of weight. Maybe sodium's electron configuration, it looks a lot, or else actually, you know what, let's not do sodium. Let's say chlorine. Maybe chlorine's electron configuration, if we were saying that chlorine was a bicycle wheel with all these reflectors, maybe it looks something like that. Maybe it looks something like that, right? And what is this wheel going to do? Well, it's going to vibrate, right? Because we haven't balanced out this reflector over here. We don't have a good balance over here. So this wheel is going to shake and vibrate. So here comes that word. Chlorine is going to want to have another electron or have another reflector on its bicycle wheel so that it stops vibrating. And that's hopefully that analogy is working for you. But the important thing to essentially get out of this video is that the most stable electron configuration is to have essentially 8 valence electrons. And that is, you can imagine when we fill up all of these orbitals, or when we fill up all of these electron configurations, let's even look at Krypton. Let's look at Krypton's electron configuration. Nearest previous noble gas is argon, so argon. And then on top of that, we've got 4s2, then 3d10, which we know isn't part of our valence electrons, but we know that this whole orbital shell is completely full. And then after 3d10, what do we have? Well, we've got 4p6. And what's something that maybe strikes you about this? Well, all of these orbitals, so each one of these orbitals, our 4s orbital, our 3d orbital, and our 4p orbitals, and essentially you could say all the orbitals that we use, all the orbitals that the electrons in kryptons use, they're all completely full. They're all completely full and balanced, and we're not looking to, we can't put any more electrons into Krypton without adding orbitals into Krypton. So that's the important thing that really lends to the stability of the noble gases. And because of that, what we're going to find, and I'm actually out of time in this video, but what we're going to find is that all of these other elements, I'll just make a big old yellow mark on my periodic table, is that all of these other elements, and I guess we can kind of include the D block. I'm not actually. You know what? Let's not include the D block. So I'm not including any of these transition metals in there. But what we can say, and what we are going to talk about in the next video, is how all of these other elements, all of our elements with 1 valence, 2 valence, 3 valence, up to 7 valence electrons, what they all want to do, essentially what will make them more stable, is if they were somehow able to change their configuration to look more, to have an electron configuration that was more like a noble gas. And most of the time, what we're going to find out is that that means having 8 valence electrons. So anyway, that's enough for this video. In the next video, I'll give you some more specifics about how these elements might go about doing that. So anyway, thanks so much for watching, and I'll see you in the next video.